Welcome, everybody. I'm Simone Thomas. I'm a researcher at the National Center for Atmospheric Research in Boulder, Colorado. And some of you may know me. I have participated in the last workshop in Nigeria on air quality, which was the first international workshop on air quality in 2014. So now I'm really excited to see that Professor Rabiu and his team is hosting another workshop, air quality workshop, here in Nigeria again. And unfortunately, we cannot participate this time in person, but we want to contribute, and my colleague, Forrest Lacey here, working at NCAR as well, has done a lot of work on air quality on Africa, and he is going to give the presentation for you. So I hope you have a great and successful week. Thank you.
Thank you for the introduction, Simone.
I'm very happy to be able to present some of the most recent results from my work here at NCAR at this conference. I would like to start by thanking all of my collaborators that are listed above, along with the National Science Foundation and the Environmental Protection Agency for providing funding support for this project. When discussing this work, a question that commonly comes up is what makes air quality in Africa a novel research project. One reason is the rate of population growth in Africa versus that in the rest of the world. This growth rate of approximately 82% between 2005 and 2030 is higher than the global rate of 30%. The growth rate is also nearly double that of India, which is a country that is often considered to be undergoing rampant growth. As for why study the air quality, that is due in large part to the impacts that ambient air quality can have on both human health and climate. According to the Global Burden of Disease, atmospheric pollutants such as PM2.5, or particulate matter that is smaller than 2.5 microns, and ozone, a gaseous species formed through chemistry in the atmosphere, have been shown to have adverse impacts on human health through inhalation. Chronic exposure to both of these species has been linked to heart disease, stroke, respiratory infections, among other diseases. In 2013, it is estimated that 10% of all deaths were caused by poor air quality, making this the fourth leading factor impacting global premature mortality. While Nigeria's leading causes of death differ from those seen in the global trends, air pollution remains as the fourth leading cause of death, accounting for approximately 8% of the total deaths nationally in 2016. With this motivation in mind, we aim to answer two questions in this work. First, can we use chemical transport models to better quantify the sources and spatial distribution of emissions and their contributions to poor air quality in Africa? And second, since Africa is undergoing a period of rapid growth and change, can we use this model information to design mitigation strategies and pathways using realistic interventions to avoid future loss of life? With these questions in mind, let's discuss how are you going to go about linking human activity and its related emissions to ambient air quality for the present day. In particular, let's see how we can use a modeling framework, in this case CAMCAM, to estimate human contributions to surface ozone concentrations over Africa. To do this, we'll be using the full chemistry version of CSM2, which is a global chemistry model that tracks the formation and fate of 220 species at the global resolution of approximately 1 degree grid cells. The model used for this work is linked to the GEOS 5 meteorology and contains bidirectional feedbacks with the land, ocean, and radio transfer models contained within the CESM framework. In order to estimate the human contribution to surface ozone concentrations, we must first model the total ozone production from all sources, shown here as R01, and then estimate the impacts from natural emissions alone, R02. One of the biggest inputs into models such as CAMCAM are emissions inventories. These inventories represent the sources of trace pollutants into the atmosphere. They can contain any number of different sectors ranging from anthropogenic or human-influenced, such as shipping, energy production, or vehicle transportation, to biogenic sources, such as volcanoes, dust, or the emissions of gaseous species produced by trees and plants. Most emissions inventories are formed by combining estimates of the occurrence of certain activities with emissions factors that represent the emissions that occur for a given event. An example of this is some of the ongoing work that I am involved with at the University of Colorado, where we measure the emissions from cooking in Ghana for a number of different residential stoves and fuels. This data is then passed into a model framework through an emissions inventory. This link is important and can provide improved model results by developing a better understanding of how local activity impacts source emissions. This chart here shows each anthropogenic sector's contribution to the total various trace pollutants in Africa. While primary carbonaceous aerosols are directly emitted as PM2.5, in a large part due to residential activities, aerosol precursors such as SO2, NOx, and ammonia have other major sources, including energy production, transportation, and industry. Ozone is impacted directly by NOx, along with a number of gaseous species known as volatile organic compounds that are not shown here, but are included in the model and have varied sources. The role of emission sources is important in understanding the spatial distribution of trace atmospheric pollutants. The image above is showing the monthly mean concentrations of surface ozone as predicted by the CAMCHEM model. We can start to see some of the regional and temporal trends based on general circulation and the seasonal influx of biogenic emissions in Central Africa. We see the peak concentrations in the Northern Hemisphere summer over the Central African Republic, and again in the Southern Hemisphere summer over parts of Angola, the Democratic Republic of Congo, and Zambia. These peak ozone concentrations align with the seasonal emissions of volatile organic compounds from forested regions, and in order to look at the purely anthropogenic influence, we must factor out these biogenic influences. This is done by subtracting out the ozone from run R02, which estimates biogenic influenced ozone concentrations. We can start to see where the human activity is leading to increased ozone, and in some areas where anthropogenic emissions lead to ozone removal. In general, the highest concentrations are in northern Africa due to the influence from transported European air, although emissions in densely populated areas like Tripoli, Cairo, and Khartoum tend to lead to ozone destruction. Another interesting phenomenon we can observe from these model results is the influence of shipping activity leading to ozone formation in the Atlantic and Indian Oceans. These estimates of surface ozone can then be used with health risk assessment models to estimate the potential impacts of this anthropogenic ozone. While the previous results purely show the estimated ozone concentrations, policymakers are more interested in quantifiable results that can be well understood by a broader audience. We will use the next section of the talk to explore the impacts from future mitigation strategies and pathways. While at NCAR, we are working on utilizing CAMCHEM as a tool for health assessment modeling. The results here were calculated using the GeoSChem adjoint model. This is a chemical transport model that runs at the global 2 by 2.5 degree resolution, but utilizes integrated exposure response functions and satellite downscaling to calculate the PM2.5 impacts at the exposure relevant scales of approximately 10 by 10 kilometers. Since this is a sensitivity model, the model output is gridded values representing the change in a specific cost function, in this case premature death from PM2.5 exposure, for a given change in emissions for each model grid cell. This framework allows for us to explore the impacts from a range of scenarios using just a present day, 2013, and future, 2030 model runs. In particular, we are interested in understanding the national scale anthropogenic emissions contributions to health impacts for both of these base cases and for proposed interventions that represent feasible replacement options by 2030. The two images above are showing the modeled annual premature deaths from anthropogenic emissions that have been aggregated to each country's individual contribution for both present day and 2030. We can see that anthropogenic emissions are responsible for around 17,000 deaths in the present day, with South Africa and Egypt having the largest contributions. As we move forward to 2030, the total population grows by approximately 50% throughout Africa, but the total number of estimated annual premature deaths grows by a factor of 5, far outweighing this population growth. In addition, we see a number of countries, including Nigeria, that have large increases in the annual premature deaths that can be attributed to anthropogenic activity. This large change in estimated premature death due to ambient air quality can be attributed to a number of factors. The first being rural to urban migration and the increased population density in cities, which are typically some of the more polluted areas. The second factor is that these health impact calculations do not include responses to relatively clean air with less than 8 micrograms per meter cubed of PM2.5. New research has shown that there is an expected adverse health outcome for exposure to concentrations in this low dose range, therefore making these results a conservative estimate of the annual loss of life due to ambient air quality. With this large increase in estimated premature deaths in mind, as scientists and policymakers, we need to start thinking about ways in which we can mitigate some of these impacts moving forward. In order to do this, we have used integrated assessment model results for socioeconomic changes in Africa to present a number of scenarios that may aid in reducing the loss of life. The first scenario uses an energy analysis from the Lawrence Berkeley National Lab, where they have identified a number of countries in Africa with available renewable energy resources that outweigh their future energy demand. If the top 12 countries identified in this report switch to 50% renewable energy by 2030, we can estimate the number of avoided premature deaths from this implementation. In general, Africa is a continent with a plethora of natural resources, including solar, wind, geothermal, and hydropower, that can put many of its countries at the forefront of implementation of renewable energy that meets their growing demands for electricity. The second scenario deals with one of the major problems that has been impacting developing countries for a number of years: transportation. Currently, there are very few controls on vehicle emissions in African countries, and studies have shown that the number of vehicle miles traveled scales with both population growth and GDP per capita growth, making it a very volatile emission sector. If we target the goal of meeting Euro 6 emission standards on all vehicles in Africa by 2030, we can use emissions models to predict the total reduction from both gasoline and diesel vehicles. This mitigation strategy aligns well with the global effort to reduce transportation emissions, which have been shown in many studies to have adverse health impacts. The final mitigation strategy is one that I have been closely working on throughout my academic career, and it targets the residential sector, specifically the use of solid fuels for cooking and home heating. This proposed scenario leverages our improved knowledge of population shifts and assumes that in urban regions all of the residential cooking emissions transition to LPG fuels, which mostly eliminate the emissions of PM2.5. By combining these reduced emissions with population data, we are able to estimate changes in emissions at the subgrid scale. Residential emissions are often a target for mitigation efforts, and the ambient air quality benefits are in addition to the household air quality benefits that are up to an order of magnitude higher in many African countries. The 3 panels above show the grid cell contributions to avoided loss of life for each of the 3 scenarios. While we see that the transportation scenario has the largest magnitude of avoided premature deaths, it is important to note that it was a continent-wide implementation, and we may expect to see similar magnitude of impacts from the energy sector if applied on the same scales. Also remember that the avoided deaths from reducing residential emissions is in addition to the avoided household air pollution deaths, making this a very attractive sector for policy targets as well. Overall, these 3 example mitigation pathways avoid nearly 50% of the total estimated deaths in 2030. One of the most important aspects of air quality modeling is to validate the results using a suite of ground, flight, and space-based measurements. In general, this is challenging in Africa due to the lack of available data and is something that we at NCAR, along with other entities, are trying to improve upon. For this specific work of better understanding emissions, we are comparing our model results to several flight campaigns and local data sources. For local sources, we have information from a number of different ground-based measurement campaigns, but most recently from a flight campaign, Dakiwa, that was done in West Africa. In terms of the regional impacts and long-range transport, we are also comparing our model results to the NASA ATOM flight measurements with the goal of better understanding African outflow over the Atlantic Ocean and in turn to the Americas. In conclusion, I hope that I've been able to give you improved information about the tools and the methods that we're using here at NCAR to understand the air quality and its impacts over Africa. Due to the magnitude of the increase in the projected premature deaths due to ambient air quality, I look forward to more discussion on the potential for mitigating poor ambient air quality as the African countries continue to develop over the coming decades. I would also like to stress the need for local observations and measurement data, which is used in validating some of these model results. This is a very important part of improving our understanding of the air quality in Nigeria and throughout the rest of Africa. With that, I would like to thank you all for allowing me to speak and wish you all to have a great conference.